Okay. All right, so what questions y'all have on the homework?
Yeah, for exam 3, what's the first homework it starts with?
17. So 17 through 20 are the homework for that one. But on 17, it looks like, what were we doing there? We were doing a lot of computation, I think, on that one, just kind of writing down the ring properties and trying to decide if it's a subring or not. That was the one with all the matrices. It's like, yeah, I could have shortened that, but anyway, you got some practice multiplying matrices, so there's that. So, yeah, so you have, that was the one with all the matrices, and then it was asking, some of you missed the question of whether or not they had identity or not, you know, so some of those matrix ones, it was asking which ones are subrings and which ones have identity, and if it has identity, what does the identity look like? So there was that. There was the one where you kind of had, you had a right identity, but not a left identity. So that's kind of interesting. Yeah, showing these are subrings. And on the subring stuff, we had the theorem 3.2, which has, you have to check 4 things. And then we had another theorem that you only have to check 2 things, right? And so, so definitely know those 2 theorems, because those are going to be ones that, I mean, you're definitely going to be asked to, okay, what kind of things are you going to be asked to do? You're going to be asked to prove something's a subring or not, for sure, right? I mean, that's something that we have been doing. You're going to be asked whether or not a map is a homomorphism, right? You're going to be asked whether or not different rings are isomorphic to one another. You know, can you give reasons why or why not? If it's isomorphic, can you come up with a map, right? So this kind of thing. What else? Yeah, so as far as proofs go, we've been doing a lot of, the proving has been like example-based proving. A lot of it has been, you know, so with this ring, can you prove this or that, you know? But then there are things about like, you know, if something is a integral domain, can you prove this or that? You know, if it has identity, can you prove this or that? You know, so some of those kinds of in general proofs happen too. Yeah.
I was gonna ask on, I think it's this most recent homework that we turned in, on proving if rings are isomorphic. They have to have all the same ring properties, right?
Yes.
So if something has identity and the other one doesn't, then it just can't be isomorphic.
Yeah, yeah, and you
Okay.
asked a question about that
Yeah.
in there. I was like, yes, you can use that for sure. Yeah, so so let's look at that problem, because several of you had different reasoning on that, which was fine. So this is 3.3.35 off of homework 20. So it's asking to show why these pair of rings are not isomorphic, right? So we have 2Z and Z. And so Julie was noting that Z has a multiplicative identity. 1 is the multiplicative identity of Z, but 2Z does not have a multiplicative identity. So therefore they can't be isomorphic. They don't have the same structure, right? I did something, I did this. Okay, what if I have a map from 2Z to Z, right? And so let's assume that F is an isomorphism. Right. So since F is surjective, there exists some A in 2Z such that F of A equals 1. So there's something that maps to 1, right? Something has to map to 1. But then you could say that, let's see, what did I say? But then, how did I get this? F of A squared is equal to 1 squared, which is 1. Yeah. But F of A squared is equal to F of A which is equal to 1 times 1, which is 1. So a squared also maps to 1, so it's not onto. So that was a little proof I had done. So what does this do? So another thing that I was seeing on these is that some of you were defining a particular map and saying this map has a problem, but that doesn't show that they're not isomorphic, right? So because what we need to show is that every map, no matter what map we do, it's not going to work, right? And so this proof does that because I haven't assumed anything about the map. I've just said it has to be onto, so something has to map to 1, and then it's going to break down, right? No matter what that something is. So the only way it doesn't break down is if A is a squared, and that only happens for 1 minus 1 and z. So, and they're not in 2z. So it's not going to work. So you have to show that it doesn't matter what map you have. It's not dependent on the map. Does that make sense? So your argument shouldn't be dependent on a particular map. But saying something about the structure, this has identity and that doesn't, yeah, that works, right? And then the other one was you have R cross R cross R cross R, which these are just 4 tuples, right? And so you can think of that as maybe a point in a 4-dimensional space, right? Or something like that. And M R, which by this notation, we need 2 by 2 matrices. I wish they would do like an M2R or something like that, so you know that it's 2 by 2, but anyway, whatever. We're just assuming they're 2 by 2. So yeah, so that's the 2 by 2 matrices. So we're saying, why are these not isomorphic to one another? And so many of you pointed out this one is not commutative under multiplication, and this one is, right? So since this one's not commutative and this one is commutative, they can't be isomorphic to one another, right? Because it's not, the multiplication map is going to break down since you don't have commutativity of multiplication. And then Z mod 4 cross Z mod 4 and Z mod 16. So why doesn't this work? Well, so we know by theorem 310 that since this ring has a multiplicative identity and this ring has a multiplicative identity, that any mapping that's an isomorphism is going to have to map identity to identity, right? And so then if you trace that out, you're going to come up with that it doesn't work, right? So if you map, so assume that F from Z mod 4 cross Z mod 4 to Z mod 16 is an isomorphism. Then by theorem 3.10, since both rings have unity, we have identity. We can use both words interchangeably. Have a ring with unity is a ring with identity. Everyone using that word? Okay, well, okay. I'll do that. Okay. Then we know that F has to map. 1, 1 to 1. Right? So F has to map 1, 1 to 1. And then if you start messing around with that, you're going to see that this is going to break down. Because if I add this to itself 4 times, I get 0. But if I add this to itself 4 times, I get 4. It's not 0, right? And so you can use the addition homomorphism part to break this down and show that it doesn't work. So another person was counting 0 divisors here and 0 divisors there and saying it didn't match up. So that's another thing you could do. So anyways, you just have to make sure that the structure of the 2 rings is the same. Yeah.
On the 0 divisors thing, I remember I said something like that, but I didn't think about it carefully. And later on, I looked and I think
they do match.
They do
Okay,
match.
I didn't actually check it either. I was just like, oh yeah, that's probably right. That makes sense. I mean, that's a reasonable thing to check, right? So I didn't actually check it either.
Yeah. But and then also another thing is I noticed that when I was looking at to one of the other problems, I assumed somewhere basically that the 0 divisors have to map to 0 divisors in isomorphism, and not necessarily.
And that's actually not true, yeah.
So not only that, I think you could have an isomorphism between sets that don't have the same number of zero divisors.
I don't think that's possible because that wouldn't be possible because the homomorphism properties would break down. So in that one that says zero divisors don't have to have zero divisors. So it's number 15, 3.3, number 15.
Oh, isomorphism, oh, I see.
Yeah. To be an isomorphism, it has to work out, right? So the reason 3.3.15 is false is because it's a homomorphism, not an isomorphism, right? If it were an isomorphism, it would have to be true. Does that make sense? So, so do you remember what 15 says? Okay, y'all don't know. Okay. So it says, let F from R to S be a homomorphism. And then we can say if R is a zero divisor in R, then is F of R a zero divisor in S, right? And so at first glance, it might seem like, well, sure, because like if R is a zero divisor, then you know that R times something equals zero in the ring, right? And so if you map it, F of R times S is equal to F of R, F of S, which is equal to F of 0R, right? Which is equal to 0S. So you think, oh yeah, so it multiplies to give you 0. But what you don't know is, are these two, to be a zero divisor, they have to be non-zero themselves, right? And so is it guaranteed that each of these guys is non-zero, right? That's what we don't know. Do you see where it breaks down here? So that's the issue. So we can come up with a counterexample. And I've only graded the people early in the alphabet. So Julie had a nice one, counterexample. What did you have there? I had a different one, but you had one that was different from my. What? Homework 20. Yeah, well, I'll show you mine and we can show you Julie's too. And maybe you worked with someone else. I don't know if you had the same as someone else, but I haven't gotten far enough to see. So if you look at this map, Z mod 10 to Z mod 5, and then this is just a kind of a naive map. We're just going to take the whatever it is in mod 10 and we're just going to reduce it to mod 5. Right? So just take the same number, but just do it mod 5. And that's our mapping. And we can prove that that's a homomorphism. It's going to work out. So if I look at 2 in mod 10, that's a zero divisor, right? Because 2 times 5 gives us 10, which is 0 in Z mod 10, right? But 2 in mod 5 is not a zero divisor, right? Why? Well, because I can't multiply 2 by anything to get 5, okay? So even that this map is a homomorphism, but where it breaks down is that when I map 2 times 5, I map F of 2, F of 5, well, F of 5 ends up being 0, right? And so it doesn't end up being a zero divisor. So that's where that breaks down. So a lot of you had this part, right? And you were like, oh yeah, it should work. But you're not guaranteed that these guys are non-zero when you do the homomorphism. Okay. What was yours, Julie?
So I did F from R cross S to S.
Okay. Oh yeah. You utilized that what we were kind of showing before, that you can get zero divisors in Cartesian products, right? So yours was F from R cross S to S. And what was your mapping?
Well,
It was F of R S equals S, right?
yeah.
So you just kind of ignore the first one, right?
Yeah.
So then you're saying that like 0, 1 is a zero divisor in our process, right? But 0, 1 maps to just 1. And this is not a zero divisor in us. Yeah, so that works. And yeah, and I like I said, I didn't get through everyone's. Others of you might have other counterexamples that were nice, but Okay, Colin?
So, okay, a lot of like the names of like types of rings that we've had, like, sort of make sense, like with identity or whatever, like it has an identity or like commutative, multiplication commutative. Is there a reason we call it an integral domain?
I know, I can never I can never remember what an integral domain is unless I'm like in the middle of teaching this course. It's just that name is so random to me. I'm sure there's a story, but I don't know it. And I agree that it's random. Or to me, it's random. And maybe once I know the story, I'll be like, oh yeah, that makes total sense. Yeah. It's kind of like, you know how Z is for the integers because there's some
Oh, yeah.
German word that starts with a Z that means integers or numbers or whatever. So there's probably a story like that about it. I have no idea. So yes.
There's a certain theorem that we're gonna need to prove on this exam.
Yeah, so you will prove a theorem, one of the theorems that we've done, but they're all so, like, the proofs are all use the similar types of reasoning. I mean, you have all these proofs that have like 25 parts or whatever, right? And each part is like not so bad, right? So I'll ask you to do like a couple of parts of one of the proofs, but I'm not going to tell you which one this time. So you don't need to go memorize all the moral of the story is don't go memorize all the proofs. Just like read through them and be like, okay, yeah, I know these kinds of arguments. You know what I'm saying? So any one of those proofs is easy enough that you could figure it out in the moment. That's what I'm trying to say, you know, as long as you're familiar with the methods. So that might not have been what you were expecting me to say or hoping I would say, but yeah, I mean, I think that the proofs that I have on the exam are things that you could reconstruct in the moment if you needed to. So as long as you're familiar with them. Okay, others from homework 20 or homework 19 or any of them?
Could you do the last one?
Yeah, I can. Were you gonna ask the same thing? Or yeah, okay. Yeah, so this is 3.3 number 41. Which I love this problem. I thought this problem was really interesting because we have worked with these maps. I mean, we were showing that Z mod 4 cross Z mod 4 is not isomorphic to Z mod 16. But in class, we showed that Z mod 2 cross Z mod 3 is isomorphic to, I don't remember what symbol they're using for isomorphic, Z mod 6, right? We showed that in class. We did the math, didn't we? And so I just thought this was a really interesting example because it kind of broke down like, why does it work in some cases and not in other cases, right? And so the reasoning, if you think about our argument here, is like, we know that the identity has to map to the identity. And if these two are not relatively prime, I'm going to end up getting 0 too soon. You know what I mean? So that's kind of the gist of the idea there. But the proof is a little bit different. So the first thing we have to deal with is a well-definedness of this. So why do we care about well-defined? Well, the reason is because we're dealing with these congruence classes. So when you have these congruence classes like this, you have to think about, does it matter what representative of the congruence class I pick? Do I get a different answer if I pick a different representative of the congruence class? That's why we have to deal with well-defined, okay? So this mapping should not be dependent on the particular representative that I pick of the congruence class. So what that means is that we have to go all the way back to what it means to be, to the definition of what it means to be congruent modulo n, okay? Or modulo whatever. So on part A, do I need to write the whole problem out or do you all have it kind of in front of you? Okay, so to show that the map is well defined, I need to show that I want to assume that A M N is equal to B M N. Okay, and I want to try to prove that. So my last line is going to be thus A M equals B M and A N equals B N. And a lot of brackets and notation there, so it's kind of annoying. For those of you who late typed all this, I mean, bless your hearts. You could, yeah, at some point you can just stop, you know, it's okay. Anyway, so this is what we want to do. And so what we're going to do is we're going to go back to the definition of what does it mean for these two congruence classes to be equal to one another? Do you remember what the definition of that was? A minus B equals, yeah. For some K and Z. So there exists some K such that A minus B is a multiple of NN, right? That's what we want. Now, how do we get to this? What do we want to do here? Well, by definition, it would have to be A minus B is some multiple of M, right? Well, do I have it? I got it, right? It's right there. Thus, we have A minus B is equal to M times KN, and A minus B is equal to N times M. So I've got it. Okay. So that's it. So you just had to break it down to go back to the definition of what it means to be congruent modulo NN, and it just falls out. That's pretty easy. Okay. But yeah, I mean, we hadn't done a lot of well-defined proofs, you know. I think we did it like at the very beginning when we first started with these things. So it's been a minute since we've done a proof like that. Okay. And part B, prove it's an isomorphism. So we have to do the homomorphism properties, right? The multiplication and the subtraction, or multiplication and the addition, right? So we want to say f of, so we want to do AMN times EMN. What does that equal? Well, that equals F, that equals, by the mapping, it's going to be AMN. Oh gosh. Some of you just dropped the brackets entirely. It's just BMN. Oh no, wait, it's multiplied. Oh right, oh shoot. Okay, come on. AM, is it M first? Yeah. BM, comma, AN, BN. So that's what the mapping says, right? Well, what does that equal to? Well, by the definition of what it means to multiply things in this kind of ring, I can split that up into two things multiplied together, right? So this is equal to AM, BM times AN, BN, right? And what's that? Well, this is F of A M times F of B, oh wait, N. Oh shoot, did I screw up? No, I got it wrong, hang on. AM, oh, AMB, oh wait, now I'm all turned around. What is my mapping? Let me write down. Okay, let me write down my mapping, and so then this will help me. Okay, so my mapping is F takes AMN to AM, comma, AN. Okay, so that's what it's doing. So I need to do this. Okay, so this is equal to AMAN, and then BM, BN. Okay, that's what I want, right? Okay, I was getting all turned around. So this is F of AMN times F of BMN. And so now I have shown the homomorphism property for multiplication, right? And then the one for addition is gonna be really similar. We're just gonna have pluses where we have timeses, right? So we can show that. Okay, questions about that? Aside from me getting all turned around? Yes.
I'm really sorry, can I ask a question on the part A really quick?
Oh, yeah,
I
sure.
didn't notice. So I think, so somehow I wound up with something weird. So the start of the problem says F is a function. We're basically supposed to show that it's well defined. Like, so the,
It's just a map. We don't know if it's a function or not. That's the point.
wait,
So showing something
Yeah,
is well defined is equivalent to showing it's a function.
yeah, it says, the start of the problem says let F be the function given by.
Oh, well, okay. But look at part A, show that the map F is well defined. So essentially what you're proving in part A is that it is a function. And so the basis of your argument was it's a function, therefore it's well defined. I'm like, well, but that's what we're trying to prove though. You know what I'm saying?
Oh.
So,
So wait, what is the definition of well defined?
yeah, so well defined is the same thing as the definition of a function.
Oh.
So it has to take, if it has, so every input has to have a unique output. You can't have you can't have a input with two outputs, in other words, right? And so for well defined, you're saying like, if I have this input that's a congruence class, I get the same output no matter what representative I'm choosing from my congruence class, right? So I can't have the same congruence class input that has a different output.
Yeah.
So.
Okay.
So the way I think of well-defined is it's basically saying that it satisfies the property of a function.
Okay.
So, but you're right, that is confusing that it says function at the beginning of the problem and then you're like part A is kind of proving that it's a function. So
Okay.
I agree with you that that's a little weird. And I think I ended up not taking out points for that.
Yeah, it looks like I didn't lose from.
And then also on part B, it says isomorphism, so the thing you have to do is to bijet.
You do, yeah, I was about to do that. Yeah. So one thing that several of you noticed is that the rings here are both finite, right? And so if we can prove that it's injective, then we get surjective for free. Or if we can prove that it's surjective, we get injective for free. So that's kind of a nice thing. But we can prove both just because, you know, why not? So, okay, so to prove that, so the surjective one is the harder one of the two. But we're gonna have to use this property that the GCD of M and N is 1, right? Okay. Also, I didn't work this out ahead of time, so I'm going from scratch here. It's fine. So for injective, what do we have to do? Well, we're gonna assume that two things over here, you know, in this Cartesian product are equal to one another, and then show that the things that they came from have to be equal to one another, right? So we're gonna assume that we have that f of A M N is equal to f of B M N, right? So what does that mean? Well, that means that I have A M A N equals B M B N, right? So I have that AM equals BM. And I have that AN equals BN. So what does this mean? Go ahead.
I was, that's what I ended up doing for part A,
Oh, yeah?
because I was using our given like F, or our given mapping, and then I used our A equals B,
Uh-huh.
AM equals BM, and then I ended up with something very, very similar to that,
Okay.
and I'm just, it's odd.
Yeah. Well, how about I look at that later?
Yeah.
Okay, yeah. And so what does this mean? So this means that A minus B is equal to MK, right? And this means that A minus B is equal to MJ for some J, K, and Z, right? And so now can I get, what I want to get is I want to get that A minus B is equal to M, oh shoot, that's an N, that's an N. I want to get that it's equal to MN times something, right? That's what I want to get. That's where I'm headed. So how can I get there? Well, I'm gonna have to use the fact that M and N are relatively prime to get there, right? Because I have that A minus B equals MK and A minus B equals NJ. So I know that MK must equal to NJ. And so M divides NJ, right? So M divides NJ. And since M and N are relatively prime, that means M divides J. Right? Right, so J is equal to MJKL, ML, right? So we get that. So J is equal to ML. So A minus B is equal to NML. So that means A minus B is equal to some multiple of MN. So that means that A MN is equal to B MN. So I proved inductive. Yes.
On the line where you have AM equals BM and AN equals BN.
Yes, did I mess
So-
up?
Well,
No, I think I didn't.
I was gonna say that AM and AN are equal to BM and BN. So can we use that to say that AM times AN is equal to BM times BN?
Yes, but what does that get you?
Well, then from the definition, I think it would give you, because like AM times BN is the same as ABN. Or
But you have different mods. You have different mods.
A times,
So you're trying to go from AM, B or AN to A, right, no, AB, wait. You're trying to go from, so you're getting A, B, M, is that what you're saying? I'm not sure what you're saying. But I'm just saying, like, we have to deal with the fact that we have different mods here. You know what I'm saying? And we're gonna have to use the fact that M and N are relatively prime. You can't ignore that. That property is what makes this map work. Right?
right.
So we've got to use that in our argument somewhere.
Okay, so what happens with, I guess I'm having trouble remembering what I was saying there, but if you just do A sub M times A sub N.
A sub M, A sub N. Yeah, you can't combine those because they're different mods, right? And I could maybe think of a counterexample if I have enough time, but I'm pretty sure that you can't just combine that.
Yeah.
We're gonna have, yeah, so we have to use the fact that M and N are relatively prime, otherwise we're kind of dead in the water there. Okay, and so if you once you get injective, then you get surjective for free because they're both finite and equal size. Great. That doesn't work if they're infinite, unfortunately, but it works for finite ones.
How is, I guess that, I feel like that's supposed to be obvious, so I'm having trouble seeing what that is. That
What
if they're
is?
finite, so we have injective means that it's like 1-to-1, like if the outputs are equal, the inputs are equal.
Yeah. So if you have, let me just do it with a small number of things. This has M times N for some M times N, right? But so that's finite. So let's just say we have, this many dots over here, and we're mapping over here to the same number of dots, right? Well, I've shown that every one of these has a unique one of these, right? I'm just gonna make them go straight across because, so what does that mean? So if there was something over here that was not hit, right? Then there would have to be, then one of these would have had to have had doubled up, you know what I'm saying?
Okay,
And so they can't double up,
okay.
yeah. So it has to be like that.
I don't know that they're the same size.
Because Z mod M cross Z mod N
Oh, okay.
has MN elements.
Okay.
So, all right, we've got like 12 minutes left. Is there anything else you all had questions on? Do you want me to do the suggested part of this? I mean, we can, but again, it's gonna depend on the relatively fine bit. So,
I'm not sure how to prove subjective maps in general.
in general, okay, so then, yeah, so why not? We can do that. Okay, so to prove subjective maps, I just have to take an arbitrary thing over in here. No, where's my map? So F takes AMN and maps to AM A. Okay, so that's my mapping. So so for subjective, I need to choose some A M A in Z mod, or I guess maybe I should just call it an A comma B in Z mod M cross Z mod N. So A is in Z mod N and B is in Z mod N. Okay, so I just picked an arbitrary element from there. And now I need to find something that maps onto it. Undefined. Okay, so if A is in Z mod M, okay, so if A is in Z mod M, okay, what's gonna map onto that? Okay, so we have the relatively prime bit, so that's gonna come into, so we need to remember, let's keep this in our mind. And we know that if A is something mod M, maybe we have we know that A is equal to M times K plus some R, right? So A is some remainder of, actually, we can assume that 0 less than or equal to A less than M, right? That A is some remainder upon division by M, right? And 0 less than or equal to A less than N, or B, B. So B is some remainder on division by N. Okay, and I want to map onto it, okay. So the GCD of M and N is 1. Okay, I'm really shooting from the hip here, I have no idea. Okay, so we get a linear combination thing. Right? Yeah,
I can't read mine anymore because I did that backwards thing where I just introduced the thing from scratch word.
oh, yeah.
But I can give you what I had and see if it comes out.
Okay, yeah, so, right, so essentially for subjective proof, we're gonna do scratch work and figure out what it is that's gonna map onto that, and then we're gonna, in the proof, we're gonna pretend that we had it all along, be like, consider this thing that I pulled out of nowhere, which you really pulled out of your scratch work, but whatever. So then you take that thing and then you show that it maps onto that. So what did you have that mapped onto it?
I had, so you have that linear combination and you want to multiply it by, what's the y-axis? Oh, you were talking about remainder thing. So I had,
We may be using different notation here, so I don't know.
oh,
Letters in it.
so the problem was, like what you're saying is we need this thing with the same A sub M and A sub N to map to a thing different, like A, B.
Right, so we want it to have, so we want to find some number X maybe, such that if I take X and I divide it by M, I get remainder A. And if I divide it by N, I get remainder B. Right, so I need to find a number that does that. Yeah.
So I said, like, if you like division algorithm, you can write that as saying like it's KM plus some Z, and it's also LN plus some Y at the same time. Like, it's like 2 division algorithms.
Yeah, that's what we're gonna need. We're gonna need two division algorithms that divide, like when we divide by m, we need to get a for a remainder, and when we divide by n, we need to get b for a remainder.
Yeah.
So did you use this notation, mu plus nb, or did you use something else?
Yeah, I use the same thing. And so once like, the thing I did was you multiply that linear combination by, the difference between the two remainders that you have when you write down your division algorithms. So whatever letter you use.
So you did a division algorithm for a?
So
So we want x to be equal to mk plus a. And we want x to also be equal to nj plus b, right?
cool, yeah. And then,
That's what we want.
yeah, and so I did.
Maybe you use different letters, but
Yeah, so basically I did multiply the linear combination by a minus b on both sides.
okay, this linear combination,
Yeah,
okay.
and then you can expand that out to get a minus b plus a minus b and b. I don't know why I switched in,
That's okay.
equals a minus b.
Hmm.
And wait, yeah, a minus b. So then your k from mk plus a
Mhm.
is a minus b times u.
A minus b times u. Really?
Yeah, because you'll have km minus ln equals a minus b.
Okay, this is ending up to being a little bit complicated. So I'm gonna stop us here because I'm not sure if this is really helping us prepare for the exam in this moment, you know what I'm saying? But anyhow, so you fiddle around with this stuff until you find an x that works, right? And then you're gonna say like, consider this x equals some random combination of a's and b's and u's and v's and whatever, right? And then you just show that it maps onto that thing, right? So x needs to have this form and it also needs to have this form. So somehow out of that, you make something that works. So that's the idea on the surjective proof. Or you can get the surjective for free by saying them on file. So there's that. So yeah, so anything else? We have 5 minutes before, yeah, so we have
On the injective portion, so we have the line A as how is that shown as an
oh, yeah, sure. So my last line was over there and then I erased it. So that's what happened.
I missed that.
So that's okay. So what does this mean? So this means that A mn is equal to B mn, right? So what did I show? I assumed that f of A mn equals f of B mn, and I showed that the inside parts were equal to one another all along. So that's inductive. Okay, so anything from homework 18 or 19? Okay, either you all are all really good or you all are all really not good, so. I'm not sure which one it is. Hopefully somewhere in the middle. Well, maybe hopefully you're good. Hopefully you're doing good. Okay, well, let's stop there. If you have any other questions that come up, please feel free. I have office hours tomorrow at 2:30. I'm gonna have to run at 3 though, because I have a master's defense I have to attend at 3. So, but from 2 to 3, come see me, or anytime, really. I'm mostly over in the MLC a lot of times, so come see me over there. Okay, you guys see if we can figure this out?
Sure.
Okay, so what is the time? Yeah, sure.
Okay.
Or anyone else shares. So you think, why does this have remainder A
So,
upon
so
division?
real quick, I can, the way I was thinking about it, and I'm not sure that the A minus B thing is actually that,
Well,
I'm not sure how hard it is to come up with that, I don't remember exactly, but basically, if you start with the idea of
I was thinking.
if you're gonna get the two, like the same representatives over there to map to like different things, mod M and S,
uh-huh.
then you're basically saying somehow we magically have a number that is, we have some number X that is A more than a multiple of M and
Right.
it's B more than a multiple of N at the same time.
At the
And
same time.
sometimes those are contradictory statements. And it's just like, if you find the examples when it's contradictory, they also just so happen to be when they're not co-prime. So I think that's why the GCD thing is.
Yeah, no, it has to be not co-prime, I mean, for this to be able to work,
So,
or I mean, it has to be co-prime. Or M and N have to be relatively prime. So,
the,
yeah, I didn't think that hard about this reductive bit.
I can try to write
Yeah, for sure.
next thing, so, so what did I just get? Oh, so, okay, so actually you don't have to say A exact thing, because you can multiply, so if you multiply this,
Yeah.
right, okay, so. So you said, K equals. I'm gonna have to stay with this. So K is A minus B. U. And
J is A minus B, B.
yes. Oh, dang it. It's negative A minus B. This is the worst way to write this. So what happens now is you have, so J is the negative of that, right?
Yeah, okay, so you subtracted it over, like so if we do X minus X, we get MKA or MK plus A minus NJ minus B. Is that why it needs to be negative?
Yeah, because so it turns into this thing. Right, it's just that
Uh-huh,
you sub K and J in, and that has to be negative because J is in.
yeah,
Um,
that's what I'm getting to.
And if you
I'm
move
getting
these
to.
over, you get KM plus B. Okay, I got the letter switch.
Yeah.
but it works. So you get KM plus B minus JN minus A equals 0.
Mhm,
So this thing minus this thing
mhm.
was 0. So KM plus B is JN plus A, which is
No,
sort of what we-
backwards.
yeah, it's backwards. So it sorts these and then set it like that.
Okay.
Which I don't think messes anything up.
I'm not sure. I'm a little turned around. I think I need some time to look at this with a clear slate.
Yeah, and I think, yeah, I'll just, yeah, I think it's kind of messy.
Yeah.
Let's check. So.
So there might be an easier way to do this that's not, doesn't have so many variables floating around.
Yeah,
You
The
know?
only-
I don't know what it would be though, but,
well, I think the only problem is if,
so what we can say is that M, okay, what about from this? Okay, so we can say that M divides X minus A. Right? And we can say N divides X minus B. Right?
Uh-huh.
And so,
uh,
so if this divides that, this doesn't share any factors of this, and this divides that.
But X minus B and X minus A aren't the same thing.
Yeah, which, that's okay, I'm just trying to think if it lets you do anything, that, like, we have this divides, and.
I
and
know,
then
I
go
know,
on.
I know, me too.
Uh,
Not sure. Yeah, I don't know. I need to think about this some more. So the subjective bit is much more difficult than that.
Yeah.
Or maybe just doing the injective and using the, and then getting the subjective
Yeah.
for free is the way to go.
And-
It might be that you got something there. I didn't wade through your whole proof. I kind of looked at it and went like, yeah, that probably works out.
Yeah, I Yeah, I don't usually like when people write proofs like that, so I'm not sure why I wrote it like that. 'cause I
Well,
don't-
it's
that's
like
not-
you didn't have a whole lot else to go on, you know what I mean? So
It's
you kind of got forced into it.
right, and so I had the wrong proof, I didn't notice the thing about the finite ring, and I had the wrong proof for, for 1-to-1.